All right, hey everyone, it's 15:15, so I'm going to start. My name is Andrew Nelson. I recently graduated from Cal Poly in San Luis Obispo, and this talk was the subject of my research as a student. I hope you guys have as much fun listening to it as I had fun learning about all this stuff. So I'm going to start off with a roadmap. First, we're going to start off with motivation. What's an example of a problem we can solve? Then we're going to get in a more general problem statement, and then how we built the solution. Then we're going to get into Funqual, which is the tool that actually enforces these call tree constraints. And finally, I'm going to talk about the application. So to start off with, here's an example of a piece of C code with an error in it. If this were a longer presentation, I'd stop and wait for someone to guess what the error is. But I'm just going to point it out. The error here, it's kind of obscure, is that we're calling printf in a signal handler. And the glibc standard kind of defines a type of function called non-reentrant, which says non-reentrant function, such as printf, cannot be called and then interrupted and called again before the first call is finished. In this case, some implementations of printf have a lock in them. If the printf in main is running while it gets interrupted, that lock might still be in hold, signal handler might start, and the whole thing would just stop on deadlock. So there's two kinds of functions here. There's preemptive functions and there's non-reentrant functions. And we already have a rule. We say preemptive functions cannot call non-reentrant functions. And in this example, it might be pretty simple. You could just tell everyone, hey, don't call printf in your interrupt handlers, or more generally, don't call these non-reentrant functions in your interrupt handlers. But this problem is actually a lot more general, and it's harder for a human to solve if the code looks something like this. So in this example, we have the signal handler at the way top. We have our actual non-preemptive call at the way bottom. And it's hidden through several layers of indirection. So you can see how asking a human to inspect and not write code like this would be pretty hard and not really feasible. Oh, there's squares now. So that's an example of a problem we can solve. Let's get into a more general form of the problem statement. What's the tool we need at a high level? And how are we going to let the user interact with it? So problem statement, we need users to be able to create their own function types. And I put function types in quotes because this isn't like returns in. This isn't the kind of type that GCC knows about. It's a completely orthogonal type system. Secondly, we want users to be able to create their own custom constraints, like preemptive functions cannot call non-reentrant functions. And we want a tool that can statically check this. And on the way, it'd be nice if we had no non-standard syntaxes. If code works with Funqual, it should work just as well with Clang or GCC. And also, it should have always correct output. No heuristics, no most of the times. There's three kinds of rules we want to support initially. The first is restrict direct call from X to Y. An example would be I want to restrict all direct calls from preemptive functions to non-reentrant functions. The next would be require direct call, which would be something like I want to require non-blocking functions to only call other non-blocking functions. And the third would be restrict indirect call, such as I want non-blocking functions to never call whether directly or indirectly blocking functions. And I should mention all these tags are as annotated by the user. Here's our three rules that we support right now. We talked about an instance of the problem. We talked about a general form of the problem. Let's talk about the things that go into this solution. So first off, if you guys haven't already used libclang to analyze source, you should try it out. It's pretty cool. Libclang comes with this Python binding library that makes it dead simple to go from code like that on the left to an AST like that on the right. And since it's just an object AST, it's super easy to traverse it and do whatever kind of analysis you want statically. In order to put things in this AST, in order to pass hints to our tool, we're going to use this attribute syntax. You guys have probably seen that square bracket syntax that's, I think, new in C++17. We chose this syntax because, well, for one, it actually gets preserved in the AST. And for two, this syntax is backwards compatible all the way back to, I think, like C89 probably. And if we wrap it up in a macro like this, then users annotating functions can be somewhat painless. So here's that original piece of code from the beginning. In this example, we would tag printf as non-reentrant. We would tag signal handler as preemptive. And then that's all the things we have to do to tell the code tool, to tell Funqual what it needs to do to enforce. The next step is creating a call graph. And using libcling, again, this is actually pretty easy. We have a piece of code like this. We're going to traverse it for every function or method declaration. We'll add a node to this call graph. For every function or method call, we'll add an edge to this call graph. And for every one of these type annotations, we're going to add a color to the call graph. And so code like this becomes a call graph that looks like that. And then once we have a call graph like this, things like a preemptive function calling a non-reentrant function can be solved easily by just asking, is there a path from a green node to a red node? Something like that. And we're all pretty familiar with graph algorithms already. There's a couple special cases with this. The first is that any and all virtual methods have to have the same type or qualified type. Just like if they had const or same return type, we're going to require the user to give them the same Funqual qualified type. And also for constructors and operator overloads, there's a little bit of finagling that has to happen with the AST to actually resolve back correctly to the function being called, but that can happen at compile time too. What about function pointers though? In this example right here, you can kind of easily see that gfunc is always going to point to bar and bar calls printf. So just by inspection, we can tell that this code is problematic. But for a lot of code, it's more complicated. We can't really tell at runtime, or we cannot tell at compile time what gfunc could refer to. So here's that call tree representation of the code we saw earlier. What we really need is some way to annotate, some way to represent that this function pointer is tainted. We're going to start with the observation that we can already tell that bar is tainted. We can tell just by looking at the code that bar could reach a red function, so we're going to mark it as tainted. And this brings up the notion of direct versus indirect type. Bar is not itself red, it's not non-reentrant, but it does reach something that's non-reentrant. So we're going to say it has indirect type non-reentrant. So now we have two kinds of types. There's direct type and there's indirect type. Functions have direct type X if they are X, and functions have indirect type X if they can reach something of type X. In the previous example, like I said, bar has indirect type X because it can reach printf. Indirect type can be inferred for functions because looking at this piece of code, we can just see by looking at the code that bar calls printf. But indirect type must be explicit for function pointers. So if we actually annotate that function pointer with indirect type non-reentrant, then it becomes obvious from the call tree that there's a call from green to indirect red, and we can say this is invalid. As far as the code goes for this, we have to annotate that function pointer with indirect type non-reentrant, just to tell it it's possible for this function pointer to hit a non-reentrant function. And if you want a formal proof of correctness, you can ask me afterwards, but this does scale up inductively as many nodes as you want. It does bring up an interesting point, though, that the call graph is only correct if any and all of these assignments are correct. So we have to enforce at compile time not only the call tree constraints, but also the function pointer assignment constraints. And these are that the direct values, or the direct types of the LNR values much match, and also that the indirect type of the L value contains the indirect type of the R value. That was definitely the most complicated part of the talk. Afterwards, it's all demo and stuff. We've talked about an example of the problem, a general problem space, talked about the tools that it takes to make a solution. Now let's talk about the actual Funqual tool, how it runs, how it works, and then we'll get to an application. So Funqual is a tool that takes in all your C and C++ source files, and it also takes in the special rules file. This rules file describes what constraints you want to constrain and any extra tags you want to add. It combines those, mixes them together, and gives you some human-readable output that should help you find these illicit calls. Things that go in the rule file are rules. There's some example syntaxes for the rules, and then also extra type annotations. And it'd be useful to put these in the rules file for like standard library functions or large libraries that you don't want to modify, but you do want to annotate. And here's an example rules file. This would be the rules file that we would use for that first example, that preemptive functions not calling non-reentrant functions. We see rule, restrict indirect call from preemptive to non-reentrant, and we see a couple of tags. In this case, I've tagged malloc, free, and printf as non-reentrant. It's easier to do this in the rules file than it is to actually modify standard lib. And we use the Clang unified symbol resolver to actually refer to these functions. I found it's the only and one of the easiest ways to uniquely refer to these functions outside the code. Running it is pretty simple. Funqual, passing the rules file, passing all the C and C++ files to run. Then the output looks a lot like this. So this is an example of a rule violation error. There is a call from a non-reentrant function, or call to a non-reentrant function from a preemptive context, and it'll tell you all the function calls in that chain. So it says signal handler on line 8, oh no, called bar on line 6, called foo on line 5, called printf, which is from standard lib. And so it makes it pretty easy to actually nail down exactly what the illicit call is that you're trying to stop. Here's an example of an assignment violation. It tells you this L value got assigned this R value, the L value has this type, the R value has this type, and it reminds you of the rule that it's trying to enforce. Here's an example of an override violation. If you tried to override a function, but you tried to change the type while you do it, it's going to give you an error. That's what the output format looks like. Let's look at some actual applications. Let's look at some actual outputs that this is given in the field. The first application, I worked a lot with a robotics group, and we kept having this recurring problem. We do controls at 100 hertz, and so every cycle had to be 10 milliseconds. We found that making syscalls in those 10 millisecond low latency areas was just a killer for performance. So what we had to do is instrument this so that it would detect calls from these low latency contexts to any syscalls. This is a snippet of the rules file that we used to actually enforce this. You can see at the way top, there's our one rule. Restrict indirect call from high frequency to slow. Slow was our simplified version of syscall. And here we have a bunch of functions tagged that all happen to make syscalls. And then when we ran the tool, it just gave us a whole bunch of output. In this specific instance, it gave us too much output to actually fix all at once, but slowly over time, we're addressing these concerns, and it's making the performance of the application a lot better. So here's another application that I did when I was in school. For a class, we were working on this super basic OS kernel from scratch, and I kept finding over and over and over again that at like kernel init time, I would keep calling functions like printf or malloc before those subsystems were initialized. And when doing kernel development, it was super, super hard to debug these errors at runtime. So I found it was very, very helpful to have a tool that could check these things statically. And what I ended up doing is I would mark functions that kind of did the initialization as pre-something, pre this subsystem, pre-MMU. And then I would mark the functions in that subsystem as the name of the subsystem, as like MMU. And then I could do things like restrict calls from pre-MMU to MMU, restrict calls from pre-serial to serial, restrict calls from pre-interrupt to interrupt. And that helped a whole lot in finding and preventing these errors. And actually, when this was deployed, I did find lots of errors that were reproducible and could be solved pretty simply. And that was a pretty cool feeling. So there are some limitations with this tool. It's kind of slow. Right now, there's no semblance of incremental linting. So it's got to parse the whole thing at once and then build the AST and build the call graph and solve it at once. For a 20,000 line project, it took about 210 seconds, which is slower than it should be. The other thing is for complicated R values, it's pretty hard to actually get correctly the type out of that. And that's just because libclang doesn't necessarily throw those type qualifiers through. It's at the declaration site, but it's not necessarily at the use site. But these are things that can be solved in the future. So there's our roadmap. We talked about a specific instance of this problem. We talked about a general case of problems, some tools that go into making the solution, the actual tool Funqual, and I showed you guys some applications. Any questions? Yeah. Oh, I guess person at the mic.
Hello. So you said that all of the derived classes that override a base class function need to have the same tag. Can you not just put the tag in the base class declaration of that function and prohibit additional tags in the children classes?
That could be done, yeah. I chose to make you explicitly annotate the overriding virtual functions because then you have to remember that I'm writing a function that has to abide by this contract. But it definitely could have been different. That was just a design choice.
Cool. Also, I wasn't here for the intro. Is this like an open source project or?
Yeah, it's on GitHub.
Cool.
It's not packaged that well right now, but.
Doesn't matter. It's going to be really useful for my company, actually. So thank you for me.
Cool.
Hi. I also think it's a really nifty tool. I had two questions. The first is there a way to specify multiple tags that might be useful in different contexts and to selectively enable and disable them?
I'm not quite sure what you mean. Can you be more specific?
Well, for example, you described tags which allow you to ensure that module initialization happens before you try to use the module. Mm-hmm. And then you also described tags around preemption. And I wonder, a function may obey both of those properties, and you may only be concerned with one of them at one time and then another one at another time.
I think I see what you mean. Well, all the tags are as defined by the user. So if you want to add a tag, you'll just make it up and make up your own rules. And then those tags, or rather, those rules, I'll go into a rules file. So if you wanted to say only enforce a handful of rules this run, you could, in theory, just pick a rules file that has a subset of your rules. And
but
if you wanted
is there a way to mark a function with multiple tags?
Yeah.
In the source file itself?
Yes.
So you can just add multiple attributes?
Oh yeah, you could add as many as you want.
Okay, great. And then the second question is, what do you do in the absence of a tag? So I know you have the external rules file to annotate standard library functions or something like that, but what do you decide as far as the constraints when a node is not tagged?
If there's no tag at all, then there can be no errors because there's nothing restricted.
So you're optimistic?
Optimistic, yeah. Okay.
So you have to be sure that you mark every function appropriately in order to get reasonable results.
Yes, but there is an idea of indirect calls. So like in this example, foo and bar are not marked at all, but it's still going to find the error, the illicit path from SIG-handler to printf.
I'll think about that. I think I know what you mean, but I'll follow you afterwards if I think of something. Thanks.
Hi, I wanted to ask, is there any plans to do it for the threads? I mean, let's say we have a function which we want to, which we want that it should appear in the call stack of only one thread. So, can it be done statically?
Should appear in the call stack of only one thread?
Right, to avoid.
I can't think of a way to do that with what's there right now. Yeah, I can't think of a way to do that, and I guess that's not in the immediate plans.
Okay.
But I'll think about that.
Okay, thank you.
Is there any annotation for untainting a function? Like if a function, for example, never calls, for example, if bar never calls printf under the condition where this is be a problem, could you annotate bar such that the indirect chain is broken?
I've been asked that before and I've thought about it. That's definitely pretty easy to implement, but I've not done the work yet. And people have suggested many use cases for that specifically. Mm-hmm. So yeah, it wouldn't be that hard to add, but it's not there yet.
Right.
Any other questions? Sure.
Would there be a way to like insert instrumentation to create? So let's say you can't prove it statically that some function is called in some context. Mm-hmm. Could you modify the tool to put in runtime like asserts for saying, maybe it like saves something into the stack frame saying, I've now been called in some context, and then later I end up being called in a context that's not allowed in that parent context.
I understand what you mean. I actually don't know what the rules are I don't know what the API is for rewriting source code. But that does seem pretty useful. So this tool doesn't support it, and it would take a lot of rewriting, but I can imagine it being useful.
Me too.
Does the AST give you enough granularity that you could annotate potentially blocks of code rather than just at the function level?
Yeah, actually. I was pretty surprised by just moving the annotation left to right by one character can make a surprisingly large difference in the AST. And I've thought about doing things like this block right here is non-preemptive, so that could definitely be done, but right now it'd just take a rewrite of how the call system's working.
Okay, thanks.
Of course.
Hey, great talk, by the way.
Thanks.
Would there be a way to prevent like recursive calls or something like that?
Yeah, you could mark a function as type X and restrict indirect calls from X to X.
And something that maybe could be recursive or not, but let's say I give a score to each function, but I could never add up to more of that, call stack.
Can you repeat that? I'm not sure if I know what you mean.
So let's say that, I don't know, each function is a 1, and I don't want any call stack that adds up more than that. To the whole
yes. This is definitely something that I've thought about before and I've needed before for like small interrupt frames, not exploding those. Mm-hmm. It's definitely possible. I just haven't put in the work to implement it. But it would be relatively straightforward to do something like that.
And one follow-up question is, from the AST, would it be possible to, let's say, compute the stack memory usage of a function and then basically add up?
Yeah, like look at how many locals there are and add up how big that stack frame must be.
At least an estimate.
Mm-hmm. It'd definitely be possible, yeah.
That would be super useful.
Just curious, can the tool track calls between different compilation units?
Yes, but you have to provide all the source at once. So it can take a lot more time for larger projects.
I have another question. In the case of the function pointers, you mentioned the function pointer has to be tagged with has to have the same tags as the functions that you're assigning to it. Mm-hmm. Have you thought about having that happen automatically? Perhaps the function pointer would be tainted with the union of all of the things, any assignment that you actually see in the program. It seems like sometimes a function pointer may point to a function that has a certain tag, other times it points to a function that wouldn't have that tag, mm-hmm. and what you care about is it might have that tag.
Yeah, I see what you mean. Right now it's set up that the LVU has to have just the superset of tags, but you're right that it could just be inferred as the union of them all. I haven't thought about that before.
The problem I see sometimes because you have the restrict and you also have the require, some tags are negative and some are positive in that sense. So unless you explicitly somehow annotate this kind of tag is a positive tag, mm-hmm. you want to union them, and you want to intersect them, and this other one's a negative one, you want to union them so that you have the most conservative analysis. You would need something like that to be able to enforce both kinds of rules.
Based on how I've done the formal verification, because the direct types must match completely, and the indirect type, one's a subset of the other, that set of rules right there works. If you were to add like a require indirect call rule, then I'd have to rethink
I'm not saying a required indirect call. I'm saying is that if your function pointer inherited, say, the union of all of the tags of any function that may get assigned to it in the program source, mm-hmm. And you have a requires clause, you would incorrectly infer that the requires clause has been satisfied.
Yes.
But in fact, what you wanted is the intersection of all of those functions, not the union, because it's a positive tag. It's not a restrict tag. It's mm-hmm. never. You would have to say if this is if it's used in a restrict sense, then it's a negative tag. If it's used in a requires, then it's a positive tag. And do the correct intersection and union accordingly, which is not hard, but you know, it's a.
You're right. It's definitely
additional
possible, but that complicates the use case quite a bit.
Yeah, it does. Thanks.
Good talk.
Thank you.
This is exciting. Thanks for the talk. But I looked at your GitHub on my phone, and I can't see a license. Is that because of my phone?
Oh.
It's not showing it to you, or have you not included one?
I haven't included one. I guess that should be the same as whatever LibCling's license has.
Oh, okay. It would help anybody who wants to use this in a corporate context if you could stick a license on it.
Sure, I'll stick one on. Thanks for bringing that up. Any other questions?
I assume it works on lambdas, right, as well?
I haven't tested it on lambdas, but it should.
I thought a little bit more about what you said. Is it possible that you might consider a rule that says every function that is invoked must be tagged, indirectly or directly? And would that prevent issues around lapses in tagging?
You could definitely make a rule like that. I still don't think I'm sure what your use case would be, because it does make sense in some contexts just to not tag a function, and in that case you're either, well, I guess I'm not sure what your use case would be.
I'll think about it and let you know. Thanks.
Okay. All right, I think that's all the questions. Is there a standard way to end these? Okay, all right, thanks.